So thank you, and thank you very much for the invitation to speak today. And thanks to everyone who I know well attending today, providing me the support. Maybe you don't know my research as well, though, so maybe this will be a good opportunity for you to see all that. And then those that I don't know you, it's nice to meet you. What I'll do today is talk about LiDAR applications, techniques for geosciences research. And I want to acknowledge a number of grad students. Now, there's other graduate students in my program that are also here that I'd love to acknowledge as well about what you all do. But for this topic here, it'll be regard to the LiDAR students. So we have another number of students that have just recently graduated, Caitlin and Steve, and were this year, and then Ryan last year, and Matt a few years ago. Matt Heyman was a student in EE, so some of you might know Matt. And then I have two candidates presently with Robert Stilwell, who's in the middle of the room there, and Katrina, is she here? No. Oh, yeah, that's right, she's in Norway at a LiDAR site. So I have two candidates. We are looking for another, so I'd like to refill this group with more students interested in this research topic. So what I thought I'd do today is cover a lot of things. But in doing so, I was thinking I would focus on one thing, but then as I work through it, I think, well, maybe people aren't interested in that one thing, maybe they're interested in something else, and then also through this, I could show you various areas of research that we do, and then build on that later if it's an area of interest. So I thought I would cover a number of LiDAR systems that we have built. I've been here 9 years. Prior to that, I was at SRI International for 14 years, and there we really started doing my LiDAR work there, and then came here to CU. And I should collaborate more with those in the EE department, particularly those with optics emphasis, and I hope to do so more in the future. Maybe this is a good avenue to get my information out so we can talk more. But so I'll go over a basic LiDAR backscatter overview of that, and then I'll start to focus in on a number of LiDAR systems that we've built over the years. So I'll talk about ArcLight, which has various attributes to geoscience applications. I'll talk about polarization LiDAR. I kind of focused on this a bit because I figured that people would be interested in that who are from in COSI, I guess. And then capable, we'll talk about that LiDAR system, another bathymetric LiDAR system that we're doing, a future LiDAR system that we've got funding from the NSF to build called Super, and then another one that's out in there in the future for a large aperture LiDAR observatory. So with that roadmap, let me just give you a construct of where our research lies. So a lot of it, it does cover the range of the atmosphere from the ground all the way up to about 100 kilometers or so. So this is where most of our focus will be today. We're hoping to extend that application to higher altitudes using LiDAR. And this is just to get you situated. There are many different types of remote sensing techniques to observe this large range and altitude. And we'll focus on the LiDAR technique for ground-based observing of the atmosphere. And I don't want to go too much in detail. We do call it aerospace environment, so as I'm in the aerospace engineering department to distinguish it from, say, atmospheric science department. But we do a lot of collaborations and a lot of atmospheric science-like work. Now, this is an actual image from the International Space Station. This is the limb of the Earth, and so you can identify the troposphere visually here. It's a little harder to identify the upper atmosphere, what we call the middle atmosphere, stratosphere, mesosphere, and this is then the upper atmosphere where it's the thermosphere and above. But there's a nice imaging fiducial here, which are very unique clouds that form at about 83 kilometers altitude, called polar mesospheric clouds. And so that helps us get a reference of altitude within this profile. There are also nacreous clouds or polar stratospheric clouds that also form here, and I'll show you an image of that later. So this is to get you acquainted, and we're going to go through this, and we're going to look at different regions of the atmosphere using different LiDAR techniques, and then we'll also actually look down on the surface of the atmosphere, of the Earth as well. Now, some of you might think of this cartoon of the boson layer. That doesn't exist in the atmosphere, but it's more of a layer that's more politically driven than it is physically driven. So to get into some background and some information about what the LiDAR systems, how they're designed, and what they're expected to do, The basic backscatter LiDAR system is what I'll be talking about today. So for the most part, the transmitter and the receiver are coaxial. They might be separated slightly, or we might actually have the beam go right in the coaxial path of the receiver, but sometimes we're a little bit off. And so we have a pulse laser system. The laser system then transmits those pulses up into the atmosphere. There's propagation to a target, and then it interacts with the target through scattering. That scattered light then comes back. It's collected by the receiver. Those photons then are recorded as electronic signals, and we start to use those electronic signals to relate their linear response to the behavior of the scatterers, as in this case going up in altitude. So this is photon counts here. I work primarily we use photomultiplier tubes for a lot of our work, so we're doing photon counting measurements. And this is an example of a measurement of the atmosphere as you go from about 18 kilometers up to about 34 kilometers. And this is a log scale, and the atmosphere is falling off exponentially with height, just due to the hydrostatic law of the atmosphere. And then we have an aerosol layer that we can probe with the LiDAR and detect and determine its details. And so that can all be wrapped up into a LiDAR equation. It's rather small, but it has a lot of information about what I just described. We can determine the range resolution, delta R, by the time of flight information, and for the given pulse width. And the information then is collected by some solid angle of your receiver, the number of photons transmitted at a wavelength, laser wavelength L, an overlap function, because if you're slightly off, you'll have a time where the transmit beam and the receive field of views do not overlap, and so you have an overlap function you may have to take care of. The efficiency, the optical efficiency, as well as the receiver efficiency, detector efficiencies are wrapped up into this term. We have a transmission both up and back, so we have a t squared. Then we have what's called the volume backscatter coefficient multiplied by the range resolution plus any noise, background noise coming into your receiver. And so all of this we need to take into account. But for the most part, what we're interested in is extracting is the physical information that's contained within the volume backscatter coefficient. And that guy is equal to the summation of all the particles in the volume at which you're scattering, the number density of those particles, and it could be a function of their size distribution, because it may not just be a single particle size, maybe a distribution of particles. And then also the differential scattering cross-section, which is dependent upon the scattering angle, which in our case, since it's backscatter, will be pi, can be dependent on the polarization angle, and also the wavelength that you're interested in receiving if it's not the same as that of which you're transmitting. So that would be inelastic, say, scattering. And really, it's this information here, it's this quantity here that connects us to the physical properties of the scattering medium. And really, the goal of what we're trying to do is to try to interact with that particle and understand better what's its properties. So with that just general background of the LiDAR systems, there's many applications of them. And it parallels the developments of radar remote sensing that precedes LiDAR, and just the light interaction with the medium enables us to look at various objectives within, let's say in this case, the atmosphere. And so elastic scattering by aerosols and clouds are usually termed as me-lidars, as the size parameter of the particle is close to the excitation wavelength. And from that, you're able to analyze aerosols, clouds, and the geometries of those clouds and their thickness and such. Differential absorption LiDAR deals with absorption by atoms, and that's often used to determine things like ozone concentration. Could also be used to measure water vapor and such. Raman LiDAR is an inelastic scattering process, and I'll show you some of that later. Also used to look at water vapor, and also could be used for determining the extinction by aerosols and clouds. Elastic scattering by air molecules, typically considered Rayleigh LiDAR, since the molecules are much smaller than the wavelength that you're exciting that scattering. And that's used for temperature retrievals, and I'll show you more about that. Resonance LiDAR, this is where we're interacting with atoms, and I'll show you a technique that we use in the upper atmosphere where we resonate with sodium atoms, and then use that information to extract information about the atmosphere from that tracer gas. And there you can get temperature, winds, and such from resonance. Doppler shift is where we could do wind lidar, wind turbulent measurements, and then laser-induced fluorescence is more when you're interacting with marine and vegetation, and then reflection from surfaces such as laser altimetry to get topography and targets. The ones that I'll be focusing on for today will be the lidar, the Raman lidar, the Rayleigh lidar, and the resonance lidar. I should mention also that this is a class that Professor Chu, who's also in our department, offers every other year, and this is a course that she goes through and does all the details of lidar remote sensing, and it has an emphasis on the atmosphere. She and I work together a lot on related projects. So for those students interested in that class, I think she offers it next fall. Now, to get right into it and take a look at one of the LiDAR systems that we worked a lot with in the past years called ArcLight. And that system is, now that I've acquainted you with the scattering properties, that system is a Rayleigh, Raman polarization resonance LiDAR system. So all of those properties now we're going to use this LiDAR system to interrogate the atmosphere with these various techniques. And they all have different purposes or different retrieval information that you can get when, based on that. This LiDAR system is located up in Greenland. It's at 67 North near Kangerlussuaq, Greenland. And this is the LiDAR beam here leaving the building. And you can see that it's green. So that's a double neodymium YAG laser, about 17 watts of green laser light. It's a lot of energy, and can be scary to work inside here sometimes when the lights, when all the reflections, when we have the walls open and we're working on it. And but we're careful, and this is the aurora, and it's a beautiful place to go to. And so the system layout for this LiDAR, we have our transmitter system set up next to our receiver system of a 92 centimeter Newtonian telescope, and then our receiver system hangs on the side. One of the bad designs about that is that every time a screw falls, once you lose a screw, it just falls right down, and then it usually rolls underneath the telescope, and then you're usually under there trying to find a little screw that fell. So I'd much prefer if this thing was more on a horizontal plane, but we had tight spaces and we had to configure it this way. A lot of students have been involved with this project. That's an old picture of me working there. And this is Matt and Katie working on the receiver system here. And then Katie taking some time off hanging out at the edge of the Greenland ice sheet, which is not very far from the site that we're at. Steve Mitchell, who's since graduated and was up at the site a number of times, worked on this system as well. Katrina Bossard, who's presently in Norway working on a LiDAR system, is doing her LiDAR research on that particular LiDAR system. Ryan Neely just graduated, but we continue to work with Ryan on a new project, so that's great. And then Robert, Robert is the only picture we had. So Robert's probably, I asked Ryan, unfortunately. But I would say Robert's one of the hardest working guys. This is just that he's exhausted himself to complete. So anyway, so on the ArcLight transmit layout, this is an old system now. This is a spectrophysics YAG laser that's 20 years old, but it still goes strong, and it's a doubled YAG system. We have a green laser, a green light coming out here, going along here, goes out to a converging mirror, which then converges this transmitted beam into the field of view of our telescope. This is the infrared fundamental part of that as well, and we also transmit that out. Before we transmit it out, we beam expand it, so we decrease its beam divergence through a ×5 beam expander, and we transmit that out. We also have a continuum YAG laser that sits over here that comes across, and it's a combination of a YAG pump dye laser, and the dye laser is tuned to 589 nanometers. That's the resonant line of sodium atom, and I'll show you some results of that. So that goes out as well. We also have a dual head YAG from Big Sky lasers, which is a cross-polarized co-aligned beam that goes out. And that comes along here, gets beam expanded, bangs along here, and goes out the system as well. And so there's some details that I have written up on here on each of those laser systems. So that's the makeup of ArcLight. And then with that, then there's a receiver layout. We have an infrared channel. This doesn't work anymore. I'm not happy with this one. Hamamatsu, well, it's, yeah, long story, but I'm not happy. This is our PMTs and coolers here. So these are photomultiplier tubes, EMI Thorn tubes. This is another PMT from Hamamatsu for our Raman channel. So we have an infrared channel. We have 532, which can be used for our elastic, me scattering, Rayleigh scattering, polarization measurements. And then we have our Raman channel for looking at nitrogen vibrational Raman scatter as well as water vapor scatter. And we also can combine this with our sodium channel and put our sodium signals in here as well. The light is collected by the telescope, and then it comes out here, goes into a motorized half-wave plate, and then gets beam splitted gracefully as we go from infrared, green, and to the longer wavelengths. We also have a Daystar mica etalon in here to help in the daytime when during the summer periods where we're mostly sunlit. We need to knock down that background signal. So I think that's just kind of a summary of the system. Let me now then show you some of the geophysical applications that we've used it for. So one study, and I mentioned these polar mesospheric clouds. These are clouds that exist at 83 kilometers. This is a picture of them on the horizon. You can really only see them. They're so optically thin that you really need to be at a time where the sun is below the horizon but illuminating 83 kilometers altitude. They can then scatter into your field of view and observe them. And they're beautiful sights. And they have a connection to climate change in the sense because their nature is that they occur in the summertime, which is kind of odd. You think that's might be odd, but it's the coldest place in the Earth's atmosphere is the summertime at this altitude. A lot of that has to do with dynamics and radiation, combination of the two. But one of the things is that when you introduce more CO2 into the atmosphere, CO2 at these altitudes becomes an infrared radiator and cools the atmosphere further. And then also to form water, it's very dry up here. So where do you get the water from? That comes from methane. Methane gets up into the middle atmosphere and gets photodissociated, breaks out, recombines that hydrogen with oxygen, and creates water vapor. And then if it gets cold enough, and we have condensation nuclei up here, then you can form those clouds. And so there's a lot of interest in trying to understand whether these clouds are growing or how they're changing and what their behavior is, partly because of the climate change area. And then also it's an interesting phenomenon to try to understand. So we were tasked to try to detect these clouds with the Lidar system. And in order for us to get to 83 kilometers altitude, we needed to put a lot of energy up, and we needed to have a large collecting aperture, and that's why we have such a large system. And so this is an example, and there's some papers that we published back a while ago observing these clouds. And so you can see that prior to this time, here's a cloud profile of one of these guys, and we can measure quite accurately the altitude as well as the behavior and the dynamics and the strength of the cloud. And this was at a time before, just recently NASA, well not just recently, a number of years ago now, NASA launched an Explorer satellite called AIM. AIM now is one that's completely focused on these clouds. And so they've got global coverage and some fantastic maps, but we were able to really get the details of the cloud basics and structure. And so that was one application that we had, and this is just a LiDAR profile here going from the ground all the way up to about 83 kilometers. And right here, we're starting to run into the noise, the background noise, and this is the profile of the molecular scatter. We have a chopper chopping the signals here, so trying to attenuate the signals as the dynamic range of the signals becomes too large and our detectors can't respond properly. And so I'm going to step through a few captured geophysical processes through the LiDAR system and show you what we can do with it. So with the ArcLight, for the Rayleigh LiDAR, so for that profile, this is the Rayleigh portion of the profile. This would be considered a me portion. This is the PMC detection right here. And this is that detection in time. So from the Rayleigh profile, we can relate the structure of the atmosphere to the Rayleigh signals that are coming back. And from that, we can derive temperature of the atmosphere at these high altitudes. And this is a plot of the temperature that's derived from the LiDAR profile. It took 30 minutes for us to integrate and get up to about 80 kilometers or so. But very accurately, we can get it down. By the time we're into this altitude range, the variance is really the geophysical variance, not the signal variance. You can see the geophysical variance as we plotted about, this was about 2 days straight of data, just plotted every 30 minutes on top of each other. But one of the things that was noticed in this data set was a very strong enhanced temperature. And Katie Greer just completed her PhD working on a full body of work to describe these better. And this is a time series now in days. And this is the altitude on this side. And this is a couple different measurement types. This is a balloon radiosonde that can only get to 30 kilometers. This is the LiDAR that completes that. And then there's another OH rotational Michelson interferometer that makes the measurements here at 87 kilometers. And so this structure, this temperature structure, was very unique, and we were trying to understand it better. And really what happens in this part of the atmosphere is that a lot of the processes are wave-driven. And so there are waves coming up from the lower atmosphere, and those waves are crashing in the middle atmosphere like waves crashing on a beach. And these waves are generated down in the lower atmosphere through jet stream modifications and orographic, wind over orographic features, and generating these waves. Well, when that energy dumps, the energy goes somewhere, and the energy has gone into these, enhancing these temperature distributions. And so Katie has done a lot of work on working with these dynamical descriptions of wave breaking and interactions that produce what we first saw in the LiDAR profiles a number of years ago. So there's a lot we can do with the thermal structure. We've done a lot of work with that through the Rayleigh LiDAR contribution. Now the system is also capable of looking at sodium resonance. So the sodium layer, it's a very interesting layer of our atmosphere, is free sodium. Sodium that is just in its atomic state, ground state, sodium. And in fact, the sodium layer shown here from our observations, also it's all alkali metals like magnesium, iron, calcium. These are left over from meteoric ablation. So meteors come in all the time. They contain those types of atoms. They ablate and leave behind the free atoms. Chemistry, plasma neutral chemistry occurs on the top side. Neutral chemistry occurs on the bottom side. But right here, this sweet spot here, the atoms are not chemically active, and so they can exist in its free atomic state. That allows us to give us a target. We can use these atoms as a target to resonate, to understand the dynamical structures that are going on here. So we use them as tracers. Although there's some really interesting information that you could also glean from the observations of sodium itself or iron itself. And so this is just an observation from the LiDAR system, just signal counts back of sodium. It's structured, it's got various behaviors, and I would defer really, I've done some work on this, and this is an illustration of that where we showed that in the presence of a polar mesospheric cloud that I showed you earlier, with the combination of the me LiDAR capability at the same time we have the resonance LiDAR capability, we were able to show that it looks like sodium gets adsorbed onto the ice crystals here and depletes the sodium layer when they're present. And but Xinzhao Chu's group does a tremendous amount of work on this. Some of them are here today, and they do a lot of work on sodium resonance, iron resonance systems, and LiDAR systems. If I have time today, I'll try to cover some of that. Now also, the other technique that we can apply is Raman scatter. This is a breakout of our ArcLight receiver just for the channel that's referring to the Raman receiver. In this case, the excitation wavelength is 532 nanometers, and that light then interacts with the nitrogen molecules We then get inelastic scattering, and we look at the vibrational Raman signals, which refer to the 607.7 nanometer wavelength. And so we have filters in our receiver system here. So that light that comes back, there's going to be green light in there, of course, just based on the Rayleigh scatter. But then we split that light out, and we pick off the 607 here on this channel. Then the other thing we do is we look for the vibrational Raman signals in the water vapor that's existing in the atmosphere. That's at 660.8 nanometers. We pick off that one, and we have it here. And the ratio of those two, the ratio of those signals allow us to estimate what the water vapor distribution is to the atmosphere. A very important property of the atmosphere that's needed, because the cloud studies, it's easier to see clouds. It's not easy to see the vapor that produced those clouds. So, this is an illustration that Ryan and I worked on this, where we took water vapor Raman measurements, which are shown in the blue. And then Ryan launched a little meteoric balloon with a humidity monitor on board, and just launched it right above the lidar, right next to the lidar system. And we overlay that here in green. So you can see that the agreement is really very excellent. We have signal percent errors on the order of 6 to 8% by the time we get up to 10 kilometers. But as you can also imagine, water vapor gets very dry in the upper troposphere. And so most of the tropospheric water vapor lies in this lower altitude here. And so we could do quite well with that. And I was first concerned about this little kink here, because it was disturbing. But then if you look at the time series of this data set, that kink is actually a demonstration of two air masses that are coming into the over the lidar system, one lower and one upper, and they're just separated by this band here. So once we got over that kink and didn't think it was an instrumental effect, of course, you spent a ton of time thinking it's that, and we felt better about it, and actually we're quite impressed by our measurements after that. And also, the balloon measurement showed it as well, so we were kind of reinforced with that. So we're able to make water vapor measurements, and those are used for understanding, particularly in the Arctic. There's a lot of interest in cloud formation in the Arctic, and so we've been able to do that as well. I'm going to just keep going over just different topical areas so that you get a broad breadth of the things we can contribute to with this kind of system. Here's another use of the LiDAR system for cloud studies. Now this is a different type of cloud system. This is what are called polar stratospheric clouds. They occur at about, let's say, 18 to 24 kilometers or so. This is a beautiful picture of them. They're pretty cool looking if you ever get a chance to see them from the ground. I haven't had that many opportunities to see them, but this was a picture that was taken from the ground. And okay, so what's important about them is that they're where heterogeneous chemistry takes place for ozone hole destruction. So when polar stratospheric clouds form, it's where the chlorine, the reservoir that contains chlorine allows for the interaction to, not saying this properly. So heterogeneous chemistry. So you've got a particle of water here. You've got a substrate, basically, that you can work on. You've got a chlorine molecule that consists of other stuff. I can't remember off the top of my head. And once that interaction takes place, free chlorine can be released. Once chlorine is released, it's a catalytic conversion where it eats away at the ozone hole. And bromine is another one. So these are very important because they serve as the center for what's going to allow for those atoms to then release and interact with ozone and start to destroy the ozone hole. So this is a measurement. Again, we're looking vertical here. We've got Rayleigh scatter happening for the most part. You can see it as the degradation of the signal goes with altitude. But we have a couple of features. We have a feature here, and we have a feature here. Now, this feature is the polar stratospheric cloud. So this is a backscatter detection of a polar stratospheric cloud. This detection here is actually of a cirrus cloud. So what we wanted to do was try to understand better their makeup. And one way to do that is to look at the polarization properties of the scattered light. And we do that here. So what we've done is we've taken two planes of polarization and we've ratioed them. And that gives us an estimate of what we call the depolarization ratio. I'll talk more about that in a moment. But the depolarization ratio gives us an idea of what these particles are made up of. As you can see in this profile, the particles that were there before clearly in the backscattered signal are not as present as the depolarization signal. They're quite low, which gives us an indication that they're probably spherical particles because they don't depolarize. While in the same instance, we get the cirrus cloud, very strong depolarization coming back off of that cirrus cloud, and we also can actually see a stratus cloud now in the depolarization signal that we couldn't really see unless we subtracted the Rayleigh signal from the data. And so these measurements help us identify what's contributing to the cloud particles. And so here's a plot again of the same data set, and then here's the day later. Another polar stratospheric cloud came overhead, was detected. The difference between these two is that we suddenly had a strong depolarization signal. When I say strong, it's like depolarization ranges from 0 to 1, so 0.2 was a reasonably strong signal. And from that, then you can start to get an idea of what might be contributing to these. These are probably type 1 small spherical, what are called NAT PSCs, nitric acid trihydrates. But as you go to type B, there are larger, more aspherical particles that are obviously present because the depolarization is going to occur when you have the aspherical nature of the cloud, of the particle. And then there's type 2 water, but we know that we weren't in that because the temperature has to be below 180 Kelvin for that to form, and we didn't have that type of temperature going on for that day. And so we can use polarization also for cloud and aerosol identification or classification. And I'm going to talk more about this type of measurement because we've done a bit more with that. So let me go over a little bit about polarimetry and Stokes vector, which, so let me just talk about that quickly to remind us about it. But we're going to spend a little more time on the polarization aspects of what we're trying to derive and what we can glean from that information. So we have our Stokes vector here in our Poincare sphere here, and that the representation of the vector of light can be displayed in this manner, where along the equator it's linear polarization, where we have horizontal on this plane, 45-degree linear polarization on that plane, and then vertical on this plane. And then as you come off that plane, you become more elliptically polarized, and then as you get to the vertical here, you become more circularly polarized. So the Poincare sphere is a nice representation of that. And also we can look at the degree of polarization by this length here, and based on this ratio of the various Stokes components. And so I want to use this now to treat the vector nature of light. So a lot of the LiDAR work that's been done before is largely dealing with is more of a scalar consideration of the light interaction and not so much the vector interaction, which is very important that needs to be considered. And so what we like to do with what we'd like to do is, if you think back when I was showing you that volume backscatter coefficient, that's where the information is. That's about that target. And so we'd like to extract information about that target. Well, that information can be wrapped up in a scattering matrix, a 4x4 scattering matrix, which from an optics perspective would be a Mueller matrix. And if we think about that, what we want to do is we want to target maybe one of these elements because they're providing us with physical information. Then maybe I can target one of these values by strategically analyzing the backscattered return. And so that can be wrapped up in called Mueller matrix polarimetry, which has a polarization state generator. So we create some Stokes vector here, and then that interacts with our scattering matrix, whatever that might be. And then we have a polarization state analyzer here. And that, I've written it only for a signal detector, so all we're measuring is intensity for that signal detector, but we need to account for the vector nature of light. And so we have this, the analyzer here is going to be most important for this row of properties here. And we can see that there's a combination of contributing factors. And so depending on how you structure your analyzer, you can start to try to identify certain scattering elements in the scattering matrix. So we're going to do that. And before I do that, I'm going to describe for you what the analyzer in this case is going to be the LiDAR system. Well, the generator is going to be the transmitter part of the LiDAR system. The analyzer is going to be the receiver part of the LiDAR system. And the targets are going to be whatever's in the atmosphere that we want to extract information from. And so we've rewritten our LiDAR equation in taking into account the vector nature of light. And so we have our Stokes vector LiDAR equation. And here, so what we have is that the received Stokes vector then is going to be dependent upon the Mueller matrix of your receiving optics. And then some of the properties that we saw before, the overlap function, the solid angle of your receiver, your resolution of your receiver, the atmospheric transmission. Here's our, I'm going to call F is going to be our scattering phase matrix. A T again is the return. We have the outgoing, I should say, and then this is the return. We also have then the Stokes vector of our transmit laser, and then whatever optics might get in the way to modify that a bit. And then we also have the Stokes vector of the background light. And so we should combine all this together to figure out what the Stokes vector is. And what we want to focus on is F, the scattering phase matrix. But we have to worry about all the other modifying effects that come along the way. And so we need to characterize our Mueller matrix description of our receiver, our transmitter, and the like. And one way we're going to analyze this is by using forward polar decomposition that has been described by Liu and Chipman. And in that case, we break down the Mueller matrix F that we had before into three constituent matrices. One we describe as being a depolarizer, one being a retarder, and the other being a diattenuator. And so basically depolarization reduces the degree of polarization and has a Mueller matrix that looks like this. If these were all zeros, then that would be a completely depolarized signal. The retarder is obviously doing the phase shifting, and so it has a configuration like this. And a diattenuator can be considered like a polarizer, and so you can have a polarizing Mueller matrix that looks like this. Now there's much more, Liu and Chipman and others have described much more detail about these matrices, but I thought I'd just write them out simply in this fashion. Now, so we're breaking it down this way because we can actually use this information for physical information about the scatterers. And so if you have a scatterer in the atmosphere, if it's randomly oriented and non-spherical axial symmetric scatterer, which actually consists, many of the particles in the atmosphere consist in that manner, then they can be represented as a depolarizing scattering matrix, which is only dependent on one parameter besides the intensity parameter of the backscatter volume coefficient. And that's the depolarization, linear depolarization value, D. So what we'd like to do then is extract that information, D, so that we can determine the depolarization of the target. And from that, we can get an idea of whether they're non-spherical or spherical targets, because that helps us determine phase relationships, whether they're solid or liquid phase. I'll talk about that more in a second. So from this, so we want to do that. So we go ahead and do that by measuring the intensity. And we had our Stokes vector measurement, but now we project that Stokes vector measurement on a 4x4 Mueller matrix that represents a polarizer. And we can have that in a couple of channels. And so this is a channel. This is a received intensity N1, received intensity N2, depending on how many channels we have, and different configurations of a polarizer. So once we have that, we can try to go after this. Now, it turns out that we only need two measurements one in the perpendicular and one in the parallel direction to measure the to provide a linear depolarization estimate of D. And so we're targeting this element of the matrix. And so by doing that and using a polarizer, a horizontal and vertical components of a polarizer, we can then measure the ratio, which is called the depolarization ratio. And to get to D, we can then take the measured intensities in the perpendicular channel and the measurement detectors in the parallel channel. And from those, come up with a value and determine whether these are polarizing or depolarizing targets. So with that information, we went ahead and built up a LiDAR system to explore the deep polar cap of Greenland and deploy a system at the summit of Greenland, which is the peak location of the ice cap over Greenland. And this is Summit Camp at 72.5 North. And Ryan Neely and Robert Stillwell have just got back from here recently and has been working on this system. And we have a new system that I'll talk about a little bit later that's going to go into the same location. But this LiDAR was designed to try to explore more about the polarization aspects and the cloud aspects and the cloud radiative transfer occurring over the ice cap, as there's concern about how the ice cap is melting and what's the cause of that. Is it radiation? Is cloud cover important for that? So there's work on that. And we've got a paper just published describing this whole system. But I'll spend a moment just showing you the layout a little bit here. So this capable system, cloud aerosol polarization backscatter LiDAR. And here we go coaxial out. Here's our transmitter on this side. Here's our receiver on this side. In this case, we're working at 523 using a ND-YELF laser. But basically, we go out and we go through beam expansion. We work the polarization such that it's linear going out, half wave plate here, half wave plate back here, polarizing beam splitter. Transmit that beam out and then collect with your Cassegrain telescope, and then have a quarter wave plate, liquid crystal variable retarder, and a polarizer combination. That combination allows us to get different planes of polarization by using this liquid crystal variable retarder. And from that, then we can get different channels of polarization information. When we do that, as I described just a minute ago, we just need these two measurements to determine the depolarizing values. So here's a sample of measurements made from the site. This is altitude here. Now these altitudes are a much lower altitude. This is from the ground up to about a kilometer or so. And this is the focus of this system. It's a smaller system. It's more focused on that troposphere and below, looking at cloud system formations and trying to understand when the different phases of clouds that are present. And so we can look at, this is just the backscatter signal right here. So we have strong backscatter here. This is actually, there's blowing snow and also clouds that are present. Here's another example where we have a cloud clearly present here in the signal. When we look at the depolarized signal, you can see here that the depolarization is very small, which means that you're not depolarizing much, which gives us the implication that these are spherical particles, not aspherical ice particles. So you can actually determine the phase of the particles, whether they're liquid or ice. And so from that, we can see that this is largely a liquid water cloud. Here you can see that in this backscatter here that the depolarization ratios are quite high, and that you get that these are ice particles here. And then we still could have liquid water describing these clouds. And so the depolarization is a nice measurement to try to indicate phase of your cloud system. However, the presumption that these clouds are randomly oriented can be raised because we know that ice particles can be oriented. And this is a beautiful picture up at summit of the consequences of oriented particles scattering. when you work out the scattering matrix for horizontally oriented scatterers, it populates these elements of the scattering matrix. So what this is indicating to us is that, before we said, well, we have, if it's only depolarizing, then it would only occupy the diagonal of the matrix. But if it's, the problem is that if the particles are oriented and you just made that assumption and we just targeted this quantity, that's going to be an error because there's a contribution to this element that is due to the scatterers, or at least some of the scatterers being oriented. So in order for us to justify that we can say that the particles are depolarizing and not dye-attenuating, then we should look for dye-attenuation elements. And if those are present, then that would indicate that these are oriented scatterers. And so our target then was to go after this particular element here by making linear dye-attenuation measurements. It turns out what we needed to do is measure 3 channels, perpendicular, parallel, and linear 45. And when we do that, we can break this down to isolate this channel, normalized by the intensity of the first element, in this manner. So whenever that's non-zero, that's going to tell us that we have oriented scatters present. If we don't have that measurement and we have depolarized measurements, we don't know if it's oriented or not. And that's an important question because a lot of the models for the climate change, or for climate studies, and for those particularly with clouds as being a major problem in these models, is that they assume randomly oriented particles. And so the question is, well, are there a lot more oriented particles? And if so, it does have a significant impact on Earth's radiation budget. Because if you can imagine that if it's more oriented, then they'll be more apt to reflect some of that sunlight coming in. And, but it depends on what their structure is, and there's not a lot known on that. But recently, the satellite Calypso had a Lidar on board that looked down and detected oriented scatterers. And this is a technique that people have used to determine whether the particles are oriented or not. And that is just that if your Lidar signal is orthogonal to the plates, and the plates are dancing around. Oh. Sorry. Yeah. So if they're oriented to the cloud, you'll get a specular reflection right back, and it'll be extremely strong, obviously, with specular intensities. And so for about 18 months, the Lidar on board Calypso was aligned nearly normal to the geopotential of the Earth. And so what happened was that at what they determined to be a 0.3 degree tilt, that the ice crystals, the oriented ice crystals, showed up in their signal in a kind of a funky way. And it's not only here, it's kind of wrapped up in here too, but they can't determine that. But anyway, they see this extension here. And then after 18 months, they said, oh, we should tilt it off maybe, let's say 3 degrees. And sure enough, those oriented ice crystals go away. The problem with them being present is that they're very strong signals, and they can really affect the interpretation of all the other measurements they're trying to make. And so sometimes it's just noise in their data that they don't want to contaminate the rest of their signals. So it was so that's one technique, is to try to be normal to the ice crystals. But another one that we've introduced, and this is a lot of Matt Heyman's PhD work, was to look at can we use dye attenuation, like I described a minute ago, to make that measurement to determine the orientation of the ice crystal. And so we did an experiment, and this is part of what Capable was built to do, and that was we can do the depolarization as you showed you previously. So here's a cloud detection with Capable. And here's a strong backscatter cloud here, and another one here. This is more of a stratus cloud. This is more of a cirrus cloud. And from that, we get large depolarization estimates. But again, we're not quite sure whether that's definitive enough. We have to ask the question whether there are other parts of the scattering matrix that are also present, other elements. And so we made a dye attenuation measurement. And what we did is we tilted the Lidar off about 11 degrees, and we made measurements off the zenith 11 degrees. We made measurements at perpendicular, parallel, and 45. And from those measurements, we can estimate, as I said before, the dye attenuation ratio. And from that, we detected during this period here and also up in here, reasonable estimates, something on the order of 0.1 to 0.2 of dye attenuation, suggesting that in some of these clouds there's orientation of the ice crystals. And it's going to be a challenge for us to figure out why there's orientation, and there's other instruments at the site that can help us do that, and that's part of our future plans with this system. But it did provide us with the first detection of doing these oriented particles through a dye attenuation measurement. And that through the measurements of all of the combinations that we can do here, we can determine whether this is actually true depolarization or is it due to the fact that there's dye attenuation present in the scatterers. We don't expect much. The other component obviously is retardants that we talked about before, but we don't expect much of that here. And Matt has gone on and for his postdoc work at NCAR has gone on and worked with them to develop, to try to measure the full Mueller matrix of the scatter, which is really what you'd love to do, right? You measure all 16 elements as best you can. The problem is that takes time, and it's signal dependent because some of those elements may not be providing much signal. And so Matt's done a really novel way to do that. It's described here in his paper here. But here's a measurement. This is made right here in Boulder, and with the high spectral resolution LiDAR system that NCAR runs. He added a rotating Coda wave plate and just tried to fill out the Poincare sphere just kind of in a random way. But by doing so, he could try to represent the various polarizations that could be used to estimate the Mueller matrix. And so here's the backscatter, here's depolarization, and then here's a very thin layer of oriented scatterers through the dye attenuation. Now we don't really know, I mean, there's a lot of, we need to understand better why things orient the way they do and where and in what process of the cloud system and things like that, but we're really preliminary in just making these measurements. But it was cool because Matt can measure a lot of the components of the scattering Mueller matrix. The dashed ones are the ones that are diagonal, and everything else are off diagonal components. And so most of the diagonal ones you can see here. So this is what's showing you the depolarization, basically, of the scatterer. This is a plot integrated. Take this, and then just integrate in time to get this. But he also shows this little blip here, which is really this dye attenuation detection of oriented scatterers. But you can also see that a lot of the other elements don't contribute. And so it actually, and in some of the measurements he's made, none of them contribute. And it's just a flat line, all the dashed lines, which is very reassuring in a way because we kind of assume that a lot of our scatterers are depolarizing scatterers and that they take on that Mueller matrix form. So, but this is a really neat way of trying to do that type of measurement. Well, I don't know how much time I have. I don't know where we're. 2 more minutes. Yeah, well, then I won't have time to go through a lot of this. So let me just tell you that we're also getting into bathymetric LiDAR. And we were looking at shallow water glacial melt ponds and trying to help in that problem. That problem here is that a lot of the LiDAR systems can't measure very well a meter or shallower because of the overlap function of the pulses and the timing that's required to make that detection. So we built up a little polarization LiDAR system to look at trying to resolve at a higher resolution than 1 meter. And we do that by allowing for the scatterers to impose the modification of phase upon scattering. So for instance, if you have a water surface here, you'll get reflection and polarization preserving. So you transmit out horizontal polarization. You scatter back. Problem is that this bottom return is also scattering back and it's kind of trailing, but they're overlapping, and so you can't get can't resolve these two. But if you can use polarization such that the first surface is preserving and the bottom surface is depolarizing, then by using 2 different channels we can separate these out. And we put that system together here called Infamous, and that's it, kind of buttoned up. And then we've done a lot of different experiments. Here's just a nice one because you can use the propagation time through water versus air. Obviously, water has a higher index of refraction. It's going to be slower going through. And so if we change the depth from 3 centimeters to 1 centimeter, can we see that difference by the expected 44 picosecond delay that's going to occur? And we went ahead and made the measurements at 3 centimeters, and we can see that we can estimate about 2.7 centimeters for that. And then we made an estimate at 1 centimeter, and we were close to about 0.6 centimeters plus or minus 0.3 centimeters. So this technique was where we used polarization to try to separate out two targets that have a changing of polarization between them. And we used depolarization in this case. So that was really cool, and we've been working more on that. We want to do more with it. It's got some great attributes that have actually led, we have a paper, but it's also led to a patent, and a company, Astra, has helped us with this and is interested in pursuing more LiDAR developments for commercial applications. There's a job opening in this area for a PhD who's interested in working on LiDAR work. Gerald's up in the back from the company back there, and he's interested to talk to anybody who's interested in this. But we also love to have students involved, and we have students that can work on this further. And just quickly, also, we're looking for students for the next phase of the capable system, which we call SUPER, the Summit Polarization Raman LiDAR. We're looking for students to work with us on, this is going to be from the ground up. We're going to build this system up, deploy the summer of 2015. Robert's heavily involved in this. We're going to go for 5 years and do more of those observing in coordination with a lot of other observing that's going on at Summit Camp. So I'd love to get the word out. We'd love to have students involved in this from design and all that good stuff. And also, ultimately, we're working with a group to develop a whole atmosphere LiDAR, one that goes from the ground all the way up to almost 200 kilometers and actually even further up to the reaches of 500 kilometers or so to get us measurements into a very difficult measurement domain. And there's a large group of people working on this. I'm part of it, which is a LiDAR project that would be going to NSF. And so there's some exciting things down the road as well for our program. So I think I'll stop here and take any questions. Thanks for your time. No questions. Oh, sorry.
So you're talking about the spatial resolution of 1 meter. I was wondering
Yeah.
if you could do better if you had shorter pulses.
Yeah, so that's what usually everyone goes to, shorter pulses, or you could do pulse compression of some sort. We had toyed with those ideas, but they built up a fair amount of sophistication on a system that they didn't really want to have a lot of sophistication to. So we were able to get down to 1 centimeter with a very simple system where the pulse lengths, it doesn't really matter how long your pulse lengths are. It just matters that you can separate out your polarization discriminator. And so the sophistication actually goes away. What we need sophisticated is the electronics. We just need a fast timing unit. But otherwise, we can have, our detectors don't need to be necessarily very high bandwidth. Our lasers don't have to be necessarily really narrow. Now, other groups are going really narrow, but it's very costly. So we're trying to go on the cheap end of things. So, all right. Yeah, thanks everybody.